Good morning, everyone. My name is Hao Ziyong. Today, I will be introducing the topic of our group project for the subject thermofluids. For this project, we were asked to choose a type of internal flow application, and after some discussion, our group decided to focus on the GE F110 jet engine. The General Electric F110 is an advanced afterburning turbofan engine developed for high-performance military aircraft. Known for its excellent thrust-to-weight ratio and adaptability, it plays a critical role in modern air combat operations. In the field of thermofluids, this engine is an ideal case study for internal flow. This engine has a 4.6 meter for the length, 1.17 meters for the fan diameter, and the weight is approximately 1,778 kilograms. The unit cost of this engine varies depending on the version and the purchase agreement, but it is estimated to be around 4 million to 5 million US dollar per unit. The manufacturer for this engine is by General Electric Aviation.
Hello, my name is Azri Saiful Iman and I'm going to be talking about the mechanisms of the turbojet engine. So the first one is how does it work? So imagine air rushing into the engine's turbine. It gets squeezed tightly, it gets compressed, mixed with fuel and then boom, ignited. This explosion produces hot gas that rushes out the nozzle, pushing the engine forward and creating powerful thrust. So we want to talk about the principle and law. So it's all about the flow. The continuity law tells us that as the engine's path narrows, the flow speeds up. Basically like that. And then we want to talk about the Bernoulli's law. The faster flow means lower pressure, helping the engines pull in air even more efficiently. So the Reynolds number. In this world of high-speed flow, the high Reynolds number tells us the turbulence rules. Well, that is good. It stirs the air and fuels together better and boosts the heat transfer. Just what a powerful engine needs. The Mach number. At one point in the nozzle, everything changes. The flow goes supersonic. When Mach is more than 1, the speed of the sound is left behind. That is when you know this engine means business. Now maybe the best part, the friction. But it's not all smooth sailing. As the hot gases zoom past the walls, the friction tries to hold them back. It causes pressure to drop and slightly reduces thrust. Still, the engine pushes on. The most critical thinking. Laminar or turbulent? This flow isn't calm. It's actually chaotic and wild. It is mostly turbulent. That is normal in engines. And when we check the Froude number, it tells us how stable that flow is. So basically, the lower the Froude, more stable flow, which is crucial in high-speed jet gas flow. Really, we move on to the language, the related formulas. So the first one is the continuity equation. So this formula shows us that if fluid flows through a pipe or engine passage, the total flow rate stays the same. It just changes the speed or size. So when the area gets smaller, the velocity increases. The second one is Darcy-Weisbach pressure loss, the name of the scientist. This formula tells us how much pressure is lost when air or gas flows through pipes or engine ducts because of friction with the walls. It is important in combustion chambers. The last one is the convective heat transfer, the Newton's law. This tells us how much heat is transferred from hot gases to the engine walls. It is important for engine cooling and thermal design.
Hi, my name is Adam Hafiz bin Abdul Hadi, and now I want to explain to you how the jet impacts work. Imagine the engine is like the big fan that sucks in air, squeeze it, set it on fire, place it out back to push the aeroplane forward. Here what it happen. First, air intake. The front of the engine drags a lot of air as a plane moves. Compressor, a set of spinning blade, squeezes the air to make it really density and hot, like a pumping up a bike tire. Third, combustion chamber. First spray into the compressor air and get it on fire. Create a super hot explosion. Turbine. The explosion rush past fan blade, spinning them like a windmill. The blades are connecting to the compressor to make it spinning. Exhaust or nozzle. The leftover hot air shot out the back super fast, pushing the aeroplane forward just like a balloon fly where you let the air out. For the simple version is like, first they suck the air and then they squeeze it. After that they do the explosion, blow and let the aeroplane fly. So that's how the jet engine make the plane fly toward the sky.
My name is Pitan Akiswakumar. In this slide, I will present the encountered problem in GF110. One of the encountered problems in GF110 is high pressure turbine seal failure. The high pressure turbine seal in earlier version of F110 engine were found to lead under high temperature and pressure, resulting in loss of internal airflow control, and premature seal failure. This issue was reported primarily in pre-1989 production F110 engines. The least affected internal flow stability, reducing overall turbine efficiency and contributing to several in-flight shutdowns and crash in the 1990s. This problem occurred because of the original seal design could not maintain tight sealing due to thermal expansion mismatches and vibration-induced wear. The internal hot gas flow lead past the seal, leading to elevated temperature in unintended areas. The resulting leakage disrupts the Reynolds number condition inside the turbine, affecting the turbulent flow behavior and increasing convective heat transfer to unintended areas. This caused component failure and internal pressure instability. The issue was corrected with a redesigned HPT seal introduced post 1989. Besides that, the encountered problem in GF110 is compressor stall and flow instability. Earlier F110 engines suffer from compressor stall and stagnation, where airflow through the compressor become unstable, leading to sudden drop in thrust or flame out. Most commonly, during rapid throttle transition, high angle of attack flight, or turbulence intake condition. This problem occurs because of the issue stem from the compressor inability to adapt to fast changing inlet air condition. This disrupts internal pressure gradients and mass flow rate, especially during acceleration. The lack of active control mechanism in earlier version allowed flow separation and pressure oscillations, leading to full or partial stall of compression state. Later version of the F110 introduced variable stator vanes and fanate, which stand for full authority digital engine control to dynamically adjust airflow and eliminate this issue. That's all from me.
Greetings, and my name is Muhammad Dani Iskandar, and I'll be taking part in suggestion for improvement. First limitation is thermal resistance in hot section. The turbine and combustion areas are exposed to extremely high temperature. Traditional material have thermal limits and require complex cooling system, adding weight and reducing efficiency. So the improvement that can be done is use ceramic metric composites (CMCS) instead of metal to withstand high temperature without heavy cooling system, improving efficiency, reducing weight and enhancing durability. For the second limitation is fixed blade design that costs efficiency. The fixed fan blade design does not adapt to different phases of flight, leading to suboptimal airflow, especially during cruising. The improvement is introduce adaptive fan blade that can adjust slightly depending on airflow conditions. This will result in a better aerodynamic performance, fuel efficiency, and reduced noise level. The third limitation is high fuel consumption at low loads. During taxi, idle, or approach phases, the engine consumes unnecessary fuel due to low thrust to fuel efficiency. So the improvement that can be made is incorporate hybrid electric assist for low spool compressor stages. This reduce fuel using during low power operation, improving fuel economy and reducing wear on engine parts. And for the conclusion, turbojet engines like the GE F10-129 demonstrate the complexity of internal flow where compressible turbulent behavior dominates performance. The engine was analyzed from structural and thermofluid perspective, focusing on how fluid mechanics govern compression, combustion, and expansion. Key factors such as Reynolds number, Mach number, and frictional pressure loss are crucial to understanding and optimizing the performance. Despite its proven power, the F110 faces challenge including thermal stress, airflow instability, and fuel efficiency. In earlier model, issues like turbine seal failure and compressor stall underline the importance of managing internal flow under dynamic conditions. Using thermofluid theory and referencing upgrade like the GE 110, 132, several improvements were proposed using ceramic matrix composite for heat resistance, adaptive fan blade design for better aerodynamic, and hybrid electric system to cut fuel usage and during low load phases. In summary, advancing turbojet technology relies on mastering internal fluid dynamics. Future design should focus on smart material, flow control, and tools like CFD to boost efficiency, reduce costs, and enhance engine durability in high demand aerospace environment. Thank you.